Oh, hello, old friend. It's good to see you. Let's talk about this word, fascination. It describes an unquenchable urge which compels our hearts to quest and be captivated. As long as there are elegant explanations to complicated phenomena, science will never lose its romance. Over the years, I've traveled the world, indulging in my fascination in physics. And now, I find that a new hunger has woken within me. A fiery need to share these great ideas with the people around me. And so, I have assembled a team of some of the greatest, most lucid, most creative minds I've encountered in my travels. And I call them my titanium physicists. You're listening to the Titanium Physicist Podcast, and I'm Ben Tippett. And now, allez, physique! Let's talk about the history of general relativity. The theory of general relativity was Albert Einstein's magnum opus. Now, most people know Einstein's name because of the work he did as a patent clerk. In 1905, a year now referred to as his miracle year, Einstein published 4 papers, one on the photoelectric effect, one on Brownian motion, one on special relativity, and one on mass and energy equivalence. A little patent clerk in 1 year proves that atoms exist, he invents quantum mechanics, and he establishes special relativity, revolutionizing all of physics. So that's why Einstein is famous. But that's not why he's great. The reason Einstein is great is because he spent the next 10 years or so inventing a theory which explains gravity. In 1916, Einstein published this theory, his theory of general relativity, and nothing has ever been the same since. Now, Einstein's theory of gravity explains the pull of gravity in terms of curvature on a surface called spacetime. Now, just the way the path of a skateboarder will weave and turn as they surf around in a skate park, Earth's trajectory around the sun can be explained in terms of bending along with the curvature of spacetime. So, it's a geometric theory of gravity. Just think, skate park. Now, Einstein's theory is kind of like the laws of architecture. It doesn't tell you what is possible, it just tells you what's impossible. Since physicists have had to rely on their imaginations to sketch out models of geometry, which can then be used to explain the gravity we see in our universe. So Einstein's theory is wonderful. It's like Lego. It gives you the building blocks, but what you build with them is up to you. Now, when was the first useful model of space-time geometry ever made? There was a man born in 1873 in Frankfurt. His name was Carl Schwarzschild. Schwarzschild was a physicist and an astronomical and mathematical genius. In 1914, World War I broke out, and he joined the German army. And in 1915, he was sent to the Russian front, where he contracted a horrible autoimmune disease called pemphigus. Then, in the hospital waiting to die, he solved Einstein's equations and came up with the space-time geometry which now bears his name, the Schwarzschild geometry. Now, you might not be familiar with the name, but you've heard of the Schwarzschild geometry before. It describes the gravity of a system where all the mass in the space has been concentrated down to a central point. In his hospital bed, Schwarzschild discovered the most powerful monster in the universe, the black hole. So today, we're going to talk about black holes and time. Now clearly, if humankind ever builds itself a fleet of mighty rockets and we march out into the darkness, we're going to come across monsters. Listen, there are always monsters in the darkness. Today, my guest is the host of the Pseudopod podcast, a show where short horror fiction is read aloud. It's Alasdair Stuart. Hello, Alasdair. Welcome to our show.
Hello, how are you doing?
I'm doing great! So on the Pseudopod podcast, Alasdair introduces each short story, but he also ends each short story with a few comments. And his comments are always really insightful and often personal reflections on the themes from the stories. In my mind, they're the highlight of each show. Now, Alasdair has recently compiled a book of short story essays based on his show postscripts, and it's called the Pseudopod Tapes. And it's probably wonderful, and you can purchase it, and you probably should, off of Amazon. In addition, Alasdair puts a lot of fun content on his blog, www.alasdairstuart.com. It's fun to read, and a link will be put up on our website if you're having trouble finding us. So, Alasdair, shall we go?
Let's go.
Woo! Okay, so, for you today, I've assembled two of my finest titanium physicists. It's the A-Team. Arise, Dr. Jocelyn Reed!
Roar!
Dr. Jocelyn did her undergraduate at UBC, her PhD at the University of Wisconsin-Milwaukee, and she's currently faculty in the physics department at Cal State Fullerton. She's a specialist in neutron stars. Now arise, Dr. David Sang! Dr. Dave was an undergraduate at UBC. He did his PhD at Cornell. He's currently a postdoc at McGill and Caltech, researching black holes and neutron stars and planets. Alright, so recently Dave has been involved in the Astro McGill podcast, where he hosts it, and recently he's talked to a guy who won a Nobel Prize. So you should try listening to that too, because Dave is great. Alright, let's start talking about time. So the topic you wanted to know about was time and black holes, and it's really interesting because, let me just give the punchline away from you.
Okay.
Let's say you have a rocket, okay? We're space travelers, and you say, I'm going to go fly down to near the edge of that black hole and take some readings. And you do, and it takes you a couple minutes to get down there, and then you spend 2 hours tooling around down near the black hole, and then you use your rocket to fly back out, and you find that 10 years has passed on my spaceship while you were out down there tooling around. The deal is that when you're near a heavy gravitational object, time moves slower. So, we can explain to you why this happens. It's entirely reasonable, but we need to take quite a long-running start, I'm afraid. But in the end, everything will make sense.
Okay, I'm strapped in.
Awesome. Okay, so time dilation. We start with time dilation. You ever heard of time dilation before?
I have.
And the twin paradox. You ever heard the twin paradox before?
I have.
Wonderful.
So this comes in just in special relativity. So just the way you have to explain how space and time play together to make electromagnetism work and all sorts of other day-to-day. If you have two people moving past each other close to a significant fraction of the speed of light, person A looks over to person B and it looks like they're moving slow compared to person A. And then person B looks back and says, actually, no, person A is the one that's moving slow.
Got it.
So you have this relativistic time dilation, which means that things that are moving fast compared to you appear to have slower clocks. And we measure this on Earth when some cosmic particles come in from distant parts of the galaxy or whatever, and they or are produced in the atmosphere and come down, and they live for much longer than if we tried to create them in a laboratory.
Wow.
So we know this happens because, we create this particle trying to sit in the laboratory and it decays in an instant. But then if it's produced in our atmosphere and it comes through and it lives for seconds. So this is like a real thing we measure.
That's amazing.
For a more comprehensive explanation of time dilation, check out Titanium Physicist episode 20. We go into it for about half an hour. All right, so let's give them names. So there's two people, Danny DeVito and Arnold Schwarzenegger, right? And Danny DeVito is in a rocket, and Arnold Schwarzenegger is at home on Earth.
And we don't understand why this movie is so good, but it is. That's the twin paradox.
Yeah, that's the twin paradox. And so the twin paradox says that, Danny DeVito, he'll take off from Earth and he'll fly past Arnold Schwarzenegger on Earth, and he'll look at Arnold Schwarzenegger's watch using his telescope, and he'll say, oh, time's moving really slow on Earth. And then Arnold Schwarzenegger will look at Danny DeVito's watch through his telescope and say, oh, time's moving really slowly in Danny DeVito's.
No, I think he'll say, time's moving very slowly on Danny DeVito's spaceship.
Yeah. So the spaceship, Danny DeVito's spaceship goes off to, Alpha Centauri. He goes almost at the speed of light, travels all the way out there, turns his spaceship around, comes back, stops his spaceship. Twin paradox says, because of this, time dilation, what happens is Danny DeVito is going to come back and he will only be 2 years older, but Arnold Schwarzenegger will be 20 years older. That's called the twin paradox.
And it's like, oh my gosh, this is supposed to be symmetrical. They both saw each other moving slowly. How the heck did that just happen?
Yeah, the very essence of the twin paradox is everybody's like, how come one is older than the other? But at its heart, in special relativity, there's kind of an asymmetry between what they see, right? So Arnold Schwarzenegger saw Danny DeVito's clock moving slowly. So from Arnold Schwarzenegger's perspective, it makes sense that Danny DeVito comes back and less time has passed for him. But Danny DeVito, when he did his flyby of Earth, he looked through his telescope and he saw Arnold Schwarzenegger's clock moving slowly, just as slowly as, vice versa. And so how come Arnold Schwarzenegger's time hasn't also been really slow? Why isn't Arnold Schwarzenegger the one who's really young and Danny DeVito the one who's really old? So that's the heart of the question. What's the difference between these two people? What's the difference between Danny DeVito and Arnold Schwarzenegger?
I had never before realized that one of the central questions in physics is exactly the same as one of the central questions in movie criticism.
It's all connected, man.
It is. It's like a beautiful mind, only without Russell Crowe, which is probably a good thing.
So here, I'll cut the answer short. The deal is that Danny DeVito doesn't experience the same things on his trip to Alpha Centauri as Arnold Schwarzenegger, right? Let's suppose Danny DeVito put his ship on autopilot. He went into a dark room and he sat quietly in his dark room.
Drinking.
And Arnold Schwarzenegger...
Drinking limoncello.
Drinking limoncello. And Arnold Schwarzenegger did the same. So he shut out all the lights and he sat in a dark room waiting for his twin brother to come home. They wouldn't have experienced the same thing, even though each saw the other person's time dilating. Danny DeVito would have experienced a much different set of experiences over the course of his trip. He would feel tremendous acceleration as his rocket accelerated him up to near the speed of light. And then he would feel a deceleration as it decelerated down and he turned around and then he'd accelerate back up again, right?
Even sitting drinking alone, he would suddenly be pushed from one wall to another wall by this acceleration.
And also by the drink.
And Arnold Schwarzenegger sits at home and he doesn't feel any of this.
He just goes on and films Expendables 3.
Right. So the moral of the story is, even though it looks symmetric in terms of the people looking at each other's watches, their experiences weren't symmetric. One of them had a clearly different experience than the other. And at its heart, that's why Danny DeVito experiences less time and Arnold Schwarzenegger experiences more time.
It's because of the acceleration that Danny DeVito experienced less time passage than
right.
Arnold Schwarzenegger.
Yes. In the end, it's not the time dilation itself that's responsible for Danny DeVito being young. It's this weird acceleration.
It was that turnaround at the end to come back that ruined everything.
Yeah. So here's the really crazy thing. So Einstein muddled this question over. He came up with a similar answer. But then he started thinking about people who were alone in rooms with no windows, drinking alone. And he asked himself, what's the difference between somebody in a spaceship in deep space with their blinds down, just drinking alone, if their rocket ship is pushing them forward and accelerating them at 9.81 meters per second squared, Earth's gravity, what's the difference between what that person experiences and what somebody experiences at home if they pull down the blinds and sit still at the table drinking?
You're pushed towards the ground right now.
Yeah, right? I mean, I feel an acceleration towards the ground, or rather the ground pushes me up with 9.81 meters per second squared acceleration force all the time. So, Einstein said, hey, what if there's no difference? What if there's no difference from somebody who's in a rocket ship accelerating, if they can't look out the ship, and somebody who's sitting at home with the blinds pulled down?
Then the internet has turned us all into space explorers.
That's right. So Einstein called this the equivalence principle. He said it's equivalent. Somebody in a rocket ship accelerating, their experience is indistinguishably equivalent from somebody who's in, say, an elevator. There are no windows in an elevator, no clocks. They just feel the push of the floor up on them with some acceleration. Now, this is absolutely bonkers, because there's no difference between somebody so if you're in an elevator and somebody cuts the cord so your elevator free falls down the elevator shaft, there's no difference from your experience up there than there is for somebody who's weightless in space. So here's the crazy thing. If the difference in Danny DeVito's time was because he was accelerating, and there's no difference between accelerating and sitting in a gravitational field, then gravitational fields must cause time to go slower.
Dun, dun, dun.
Surely that means time flows slightly differently on every single body that exerts a gravitational field in the universe because they're not of a uniform size.
Correct.
Not only that, but it also depends on how far away you are from the center. So on the top of a skyscraper, you're a bit farther away from the center of the Earth. You actually feel a little bit less gravity than someone who's like standing down on the street below you. And that person down on the street below you is experiencing a slightly slower flow of time.
My God, this explains why so many of the Starfleet officers responsible for plotting Stardate ultimately killed themselves. There's no way to do so accurately.
That's right.
That's amazing. So time is actually subjective. It changes not only depending on the individual, but on the individual's location.
We have to actually include this effect in your GPS.
Yeah.
Your GPS is based on careful timing of pulses from different satellites. So you actually need to take into account how far up the satellites are compared to how far you are, and take into account all these little differences in how time is flowing, both because of the gravitational potential and because of the relative speed of satellites whipping around while you're staying on the surface.
Is this one of the reasons why GPS satellites tend to be parked in geostationary orbits, to try and mitigate this kind of effect?
No. So it's, in essence, how does GPS work? They're just clocks above the Earth in an orbit, and they're just broadcasting the time. They're just saying, beep, the time is now 5:08, 1 second p.m., beep, right?
Plus 32.
Plus 32,015, yeah. So the deal is your GPS receiver, it knows where all the satellites are. They're in geostationary orbit, so it knows the location of all these satellites. So if it hears the time from 2 or 3 different satellites, it can calculate the amount of time it took for that radio signal to get broadcast down to Earth. And from that triangulation, it can figure out where your location on the Earth is.
But in order to do that, the satellites have to know very well what the time is.
Yeah. So the deal is way up high, up in space, far away from the Earth, the pull of the Earth's gravity decreases. So time is moving slightly faster up there. So they had to include a calculation to compensate for the fact that gravity is less up in space, because otherwise the clocks would be moving too fast and all the GPS locations would go wonky because we wouldn't be able to accurately use the time to triangulate our location because time's moving slower up there to so many decimal places.
That's so unspeakably brilliant, I'm almost at a loss for words. That's amazing.
Science!
Science, exactly. So the thing which we're taught is a universal constant is only a universal constant because of lots of frantic maths.
Yes.
Yes.
Oh, I owe you guys a drink, and by you guys I mean not just you, but possibly every scientist ever.
Yay.
That'd be quite expensive. Some of these people can drink a lot.
He said 1 drink per scientist, not that he could buy everybody drinks so they got drunk.
So now we can actually talk about how time changes near a black hole. So very close to a black hole, you have a lot of gravitational acceleration. For instance, in Doctor Who, there's an episode, I believe, called The Satan Pit, where the 10th Doctor, David Tennant, goes and meets the devil. And the devil is being kept in a prison that is suspended beyond, pretty close to a black hole.
Yes, as if I remember correctly, it's actually orbiting one.
So the Doctor and Satan should both experience time going much more slowly for them than how other people would experience it far away from that black hole. In this case, that close to a black hole, time would run 20% slower for them than, say, Rose sitting in the TARDIS up far away from the black hole. So luckily, the Doctor has a time machine, and so he can always correct for these kind of factors. But I don't think they took that into consideration in the episode. So let's say the Doctor is talking to Satan for about, 4 minutes. Rose will see the Doctor talking in a much huskier voice for 5 minutes.
I think you need to demonstrate the husky voice, Dave.
We'll wait.
Instead of allons-y, he'll say, allons-y.
Ooh.
Oh, smooth. I like that.
That's why Satan has such a deep voice, because he's hanging out next to a black hole. He actually talks like this most of the time.
Satan is Mickey Mouse. This makes an awful kind of sense now. Come on, Bruno. Souls to harvest.
Right. So this is actually how we can actually measure this whole thing about time traveling closer to the surface of things, not only for GPS satellites, which requires incredible precision, but we first measured this almost a century ago when we were trying to understand how big certain crazy-ass compact stars were. So do you know Sirius, the brightest star in the sky?
Yes.
It has a white dwarf that it orbits with. So that's Sirius B. Mm-hmm. And this was the first time that people kind of figured out what white dwarfs were. And so they tried to measure the shift of wavelengths of certain features in the white dwarf, in the companion of Sirius. So they look at Sirius. Elements have kind of a fingerprint of wavelengths that they like to absorb or emit. Okay, so they have a precise frequency that they're going to either absorb light or emit light at. And you look at these elements in both the main star and in this little tiny companion star, and you find that the companion star, the wavelengths have been shifted so that they're at much lower frequency. So just like the devil is talking in this super low voice, the wavelengths from these elements have been shifted to a much lower frequency when they measure it.
Because of the time dilation.
Exactly.
So even after you correct for all the relative motion between the two stars, you see this time dilation effect.
So normally we talk about Doppler shift from relative motion, right? So if like a car goes by with its motor, you get the sound, right? And then so it's the high pitch when it's coming at you, and then when it's going away, it has a low pitch. That's the same kind of frequency shift. With Sirius, it's got the kind of frequency pitch that makes it seem like it's moving away from you at 80 kilometers per second, except it's staying right beside its companion, Sirius.
Got it. Okay, I see that. That's, again, sort of amazing, because what I'm seeing from that is lots of echoes of larger processes at different levels of the universe. Like you mentioned, Doppler shift, redshift, blue shift, I would imagine being the visual equivalency for that. So you have this, you can actually measure the impact of time dilation by the frequency of the star. That's really interesting to me, because one of the things which I studied for a very small amount, a massively amateurish amount of time, was the history of planet hunting. And how, I think at least 2 occasions, the next planet out in the solar system was found by looking not for it, but for the gravitational distortion in the furthest planet out's orbit. So the idea of being able to measure time dilation by looking at something which it causes rather than by looking at it is something which I can kind of clasp onto that way. That's fascinating.
So something even cooler happens as you approach a black hole. The time dilation actually becomes infinite as you get to the what's called the event horizon.
You ever heard of an event horizon before, Alasdair?
Yes.
Okay. So we've said before that every massive object kind of has a Schwarzschild geometry, okay? And the deal is not every object, like the Earth, isn't a black hole. It doesn't have the black hole geometry. And one way to imagine it is the Earth will be of a certain mass. And so if you were to draw the curvature of the Earth, you could just draw this big curvature in a sink, and then you just fill up the sink with water up to a certain height. So the deal is that we only see the part of it that's outside the water, metaphorically. And so what happens in gravitational collapse is it's kind of like you drain all the water from the sink. The surface of the star or the big object collapses down and exposes more and more and more of the geometry. And so you can talk about locations in the geometry in terms of how much acceleration you need to stand at that point, right? So right now I'm standing on the surface of the Earth. There's 9.81 meters per second squared of acceleration on the surface of the Earth. Now, if I took the Earth and I shrunk it down to half its radius, so I took my big Hulk hands and I wrapped them around the Earth and I crushed it down to half its radius, then the force of gravity to stand on the surface of the Earth would be, 4 times higher than it is right now. Okay? And so the deal, so it's just kind of like you imagine the surface receding. So if you have a cataclysmic gravitational collapse, like the kind that makes a black hole, the surface will recede down and as all the matter collapses down to a point. And all that will be left is this big curved sink. And so there's going to be a radius in this curved sink where the acceleration due to gravity is so violent, so fast, that not even light will be able to escape away from it. If you move just a little bit inside that radius, what will happen is, since not even light can escape, you can't go the speed of light, so you have no hope of escaping. So you'll probably get sucked down into the middle. And so that boundary between the inside of the black hole where you're going to get crushed to death and the outside where you still have a chance to see your loved ones again, that's the event horizon. So the event horizon's lots of fun, and the deal is it takes an infinite amount of acceleration to stay. So you'd need a rocket that was turned on full blast and exerted an infinite amount of acceleration to stay at the radius of the event horizon.
There's a point where you're still not at the center, but it takes an infinite amount of acceleration to balance gravity.
And then so if you and I, Alasdair, had rocket ships, if I was in some orbit at some really, really high radius, so I hardly feel the force of gravity on myself, but you wanted to do some measurements, you took your rocket to really close to the event horizon, to keep from falling in, you would have to exert an intense amount of acceleration, like 100 billion Gs of acceleration to keep from crossing the event horizon and getting crushed to death. And so the course of you going down and then coming back, you undergo so much acceleration that you personally will feel much, much less time passing than I will waiting for you to come back.
And we're back to Danny DeVito and Arnold Schwarzenegger.
Or Satan.
Yeah, or Satan.
Or Satan and the Doctor.
Or the Doctor and Rose.
Yeah.
Let's say that Satan's prison is actually extremely close to the event horizon. And I think the Doctor actually went down by a rope, which doesn't make any sense. But let's say that Satan's prison is really, really close to the event horizon of the black hole. The Doctor spars with Satan and then escapes back to the TARDIS, only to find that Rose has basically lived her entire life, died, and is now a pile of dust.
Right.
Because the dilation is so accelerated because it's a black hole.
Because the gravity is so intense near the event horizon that the Doctor's experienced time pass much, much more slowly.
Just sort of similar to the way the acceleration becomes infinite, the amount of time dilation is also going to become infinite as you pass the horizon.
So we're well into the old thing of the frog hopping towards a pond, and each hop is half the distance of the last one, so it never actually gets that.
So that's what someone looking at you from outside.
Right. So let's say Arnold Schwarzenegger has just had about enough of Danny DeVito and has basically thrown him into a black hole. You're going into a black hole. And he falls into the black hole. Now Arnold, sitting there, watching Danny DeVito fall, will see Danny DeVito get closer and closer and closer to that event horizon. But because the time dilation is occurring, 1 second for Danny DeVito will be longer and longer and longer for Arnold Schwarzenegger. So
Danny DeVito is going, "Wah!"
And Arnold Schwarzenegger will actually just see Danny DeVito get stuck at the event horizon and very quickly redshift away.
Yep. He'll never really see Danny DeVito crossing the event horizon. He'll just kind of see him freeze in place and then slowly get redder and redder.
Like at the end of an 80s movie.
80s pre-end credit sequence freeze frames being used to explain time dilation in black holes. Yeah, I'm hugely impressed. I can see that. So
where are they now? And then at the end it says, Danny DeVito is in a black hole.
Arnold Schwarzenegger was found not guilty for murdering Danny DeVito, as technically he isn't dead and never will be.
Yeah, nice. Of course, the other crazy thing is Danny DeVito just falls through without noticing anything particularly different about the horizon.
Well, in essence, that's still an application of the equivalence principle, which is that if Danny DeVito's not accelerating, if he's in free fall the whole time, he might as well just be floating out in space. And so he doesn't ever notice that he's crossed the event horizon, even though from somebody standing outside the black hole, it takes him an infinite amount of time to cross. The universe ends before Danny DeVito can cross that event horizon.
And this is assuming that the black hole is large enough such that Danny DeVito doesn't get turned into spaghetti, which was the topic of another show.
Yeah, we talked all about spaghettification.
So, you see Danny DeVito going, "Rah," but Danny DeVito is going, "Ah," the whole time.
Yeah.
Just like he does now.
Moving at a different speed for him.
Well, that was fun. I thought that was really neat. So thank you, Dave. Thank you, Jocelyn. You pleased me. Your efforts have borne fruit, and that fruit is sweet. Here's some fruit. Dave, you get a persimmon, the longest aging fruit in the world. And Jocelyn, you get an eggplant because they're black.
What?
Eat it. Enjoy it.
But can I assume it's roasted?
Yes, sure.
Okay.
Good. Wonderful. All right, I'd like to thank my guest, Alasdair Stuart. Thanks, Alasdair.
Thanks for having me on, guys. It's been great.
Oh, I had so much fun with you. We'll have you on again in the future.
Fantastic.
All right, so hey, TIE Fighters, that's you. Listeners of the show are called TIE Fighters. Everybody gets that wrong. Dave, it's your fault. Listen, TIE Fighters, I love the show, and I hope you do too. But for every listener to the show, I know that there are 100 other people who would love to listen, but they don't know how. And I want you to spread the word. There are 3 ways you can do this. The first is iTunes. iTunes is still the biggest place people go to find new podcasts. And iTunes puts the shows with the most ratings at the front of the queue where everybody can see them. So, if you've got a minute, give us an iTunes review. It'll increase our rank and more people will be able to discover us accidentally. The second way is to teach people how to listen to podcasts. I know this sounds weird, but everybody nowadays has a smartphone or a tablet. But a low percentage of these people actually know how to listen to podcasts. So if you know somebody who might like the show, ask them if they know how to listen to podcasts. Chances are they won't. And if they don't, put them to the Stitcher app. Because the Stitcher app is free and easy to use, and it works on every handheld device. So surely your grandmother will thank you for it. Now, the third way to spread the word is to tell people online about us, because the internet is full of people trying to explain physics. So if you see someone on the internet talking about a topic that one of our episodes covers, post a comment telling them about the show. It'd be nice if people started treating podcasts in general, even like ours, as reference material instead of just fun one-shot entertainment. Okay, that's it. I hope you'll help us out to point new listeners in our direction. Thanks. That's it for the main part of today's show. Remember that if you like listening to scientists talk about science in their own words, you might also like listening to other shows on the Brachylope Media Network, like the Weekly Wienersmith, where Kelly and Zach Wienersmith talk to academics about their research. Or you might like listening to Science Sort Of, where we talk about science in the news. So, editing support for the Titanium Physicist podcast is provided by a gentleman named John Heath. Thanks, John. Now, the intro to our show is by Ted Leo and the Pharmacists, and the end song is by John Vanderslice. Until next time, good day, my friends, and remember to keep science in your hearts.
I gotta tell you, dear, before you come back here. I lost your bunny. I let him out of the cage. He was eating spring mix on the carpet. Jumped through a window out into the haze. Hop down Magnolia Boulevard. No way he'll survive.
Yeah, and do you have any questions to start the show? We thought we'd start talking.
Yes.
Yeah, okay. Hit me.
Yeah. The Schwarzschild geometry.
Yes.
This is an interesting one because an awful lot of the science programs I've seen have represented space-time's geometrical shape as a flat sheet, and how gravity will distort that depending on the size of the object which the gravity is being exerted by. At the risk of completely destroying any possibility of describing this in audio rather than visually, how does the Schwarzschild geometry differ from this flat, slightly lumpy sheet?
A lot of the time, the way you make a picture of the Schwarzschild geometry is you try and take a cross-section through the black hole. Okay, so you try and take a slice, and far away you're just making like a flat piece of paper, say, that would slice through it. But then as you get towards the black hole, what you end up with is something that looks kind of like a funnel that just then extends down forever in the middle. This is what you would see no matter which direction in space you made the slice, and it also kind of ignores what time is doing. But this is similar to the kind of picture you make if you take this rubber sheet analogy and then you put, you just punch as hard as you can down the middle of it until it just goes down for infinity and it tears and you don't really know what's going on. That funnel shape is the kind of geometrical model you can think of as a black hole analogy.
So if you just looked at a black hole, it would appear round. Or looked at a Schwarzschild black hole, it would appear just as a round sphere. Mm-hmm. And it's really just this slicing. The analogy with the bent rubber sheet towards this funnel is really just a slicing of that black hole. So we take a cross-section, and it allows us to see sort of the structure of a four-dimensional object in 3D space. Just like, you can see a 2D structure of orange when you slice it, even though the orange is really a 3D object.
Or if you see those cool, slices of humans.
Yes.
Where you can see inside them.
When you slice them?
There's various... There's medical imaging things, or they've done this with actually people that have donated their bodies to science after they've died, and they go through and slice it in thin sheets.
Oh, after they've died.
Key point there. Unless we're going to go back into the horror story side of this podcast. But so if you tried to do that with a black hole, you wouldn't get a flat sheet anymore because the space itself gets all wobbly and deformed in the middle.
It's kind of hard to describe. Usually when they do it on, say, television, and you see this bent sheet, they're doing it because one of the main intuitions that general relativity, this geometric theory, brings is it explains why things are in orbit. Okay, so in Newtonian gravity, in Newton's picture, he imagined that there were something like angels with invisible strings. And, there was a string that goes from the Earth to the Sun, and there are angels inside the Sun dragging the Earth to the Sun, and they're applying a certain amount of force, which depends on distance, which then causes the Earth to travel in kind of an elliptical orbit.
Same as if you had a rock on the end of the string and you whirl it around your head and it keeps going in the circle.
Right.
The gravity is an invisible string in the Newtonian picture.
But in the general relativity picture, there is no string. So instead of being pulled in on a string, what's happening is the sun causes a deformation in space-time. So it causes space-time to be smushed in some particular way. And then what happens is the definition of how a straight line lies in the space-time becomes all wobbly and curved. It's like taking a pencil and drawing a straight line inside of a sink. You can take a felt marker and draw a straight line in the sink, look really closely, make sure your line is really straight, but then when you take your head out of the sink, you look down at your straight line, and it's a curve.
You need to start out with one of those curvy bathroom sinks. If you did it in a flat, industrial sink, it wouldn't work.
Or maybe a bowl. But...
Yeah, all right.
Oh,
so
bowls.
A bowl.
Yeah, draw your line in a bowl.
Line in a bowl, got it. Okay.
I guess.
You're really mixing your drug metaphors here, actually.
If you got a bowl and you try to draw a straight line, what'll happen is that straight line, even though at all really close microscopic inspections the line is straight, when you take your head out of the bowl, the line ends up curved. And so the reason the Earth is going in a circle kind of around the sun is because the very nature of straight lines around the sun becomes curved in on themselves.
So the thing which I'm kind of taking away from this is threefold. Firstly, Fringe may have lied to me, which I'm not super happy about. Secondly, it strikes me that what you guys do for a living is actually at one more remove than I ever previously thought. It's not that you're kind of looking at this stuff, how best to describe this, directly. It's the models, the geometries are put in place, almost like glove boxes for radioactive materials. They are the things which you use to deal with the forces which cause the stuff, but you only ever see cross-sections of it. So it must almost be like intimating a large picture from a small section of it. Well, and that has never occurred to me before. That bakes my noodle. I'm kind of blown away by it.
So space-time itself is a four-dimensional construct, and our pitiful human minds can't really picture 4D very well. So we can use mathematics to describe that, and then to get a picture that we can actually look at, that's when we take the three-dimensional slices of four-dimensional space.
So it's actually a four-stage process. It's maths, model, interpretation. Am I right?
Yeah.
I feel smarter already. Thank you. That's amazing. The other question which I have, which directly relates to that, it's kind of a twofold one. Firstly, how does gravity wells, as generated by planetary bodies, how do those relate to the curvature of space-time? And is that relationship more complex than simply the bigger the body, the bigger the gravity well, the heavier the curve?
So the deal is that every massive object, close in enough, the Earth, the Moon to some degree, Jupiter, the Sun, causes a space-time curvature that looks like the Schwarzschild curvature. So they all look like this funnily, sinky thing.
Mm-hmm.
Now, the difference between the Sun's and the Earth's is just a matter of scale. The mass of the Sun causes a lot more curvature than the Earth. But if you get really close to the Earth, as we are now, the curvature that's caused by the Earth, so our attraction to the Earth, is much larger than our attraction to the Sun, which is why we're stuck to the surface of the Earth instead of getting sucked into the Sun.
So Einstein's equations actually say that space-time curvature is sourced by matter and energy, and that if matter and energy is present, it will bend space-time around it. For the Schwarzschild solution, he just found the special case of this, where if you have a whole bunch of matter at a single point, this is how space-time will curve around it. So for planets and the sun and stars and everything, most things, you can approximate this by the Schwarzschild solution to a certain degree.
As long as the mass is in a sphere, then outside of the mass, it looks exactly like the Schwarzschild.
Well, as long as it's not rotating.
As long as it's exactly in a sphere. Right, and I mean, a rotating black hole doesn't look like Schwarzschild either, but as you know, outside of a planet, outside of a star, outside of a black hole, you can't immediately tell by the shape of space what's in the middle.
Right.
That's interesting, because that leads into two other questions for me. The first one is, obviously, my inner science fiction writer, when you say provided the matter is in a sphere, immediately goes, but what circumstances would lead to it not being in a sphere?
So the Earth isn't a perfect sphere. It's kind of a squished. Yeah, like an orange.
In fact, we have satellites that fly around the Earth that measure the gravitational variations to see how much the Earth does deviate from a perfect sphere. And that can, those sort of density variations can tell us about where minerals are deposited.
Sometimes they can tell us where matter is distributed, but I mean, Dave also mentioned things that are rotating. And, you know, if you rotate, the Earth is actually kind of pulled out a bit at the equator because it's spinning around. So if you spin something, you feel that centrifugal force. And so the equator of the Earth actually gets pulled out a little extra. So Earth isn't a perfect sphere because it's spinning. And so whenever things spin, they tend to deform a bit from that kind of force.
Got it.
In fact, when you have objects spinning, they actually tend to drag space and time around with them very slightly. So a spinning black hole will actually drag space-time around with it. So if you were just sort of sitting still around there, you'd get dragged by that spin.
Wow. So it's similar to, in terms of motion, in terms of effect, similar to the spin on a galaxy that deforms the arms around as it rotates, or on a much smaller level if you have a water wheel and, you know, the paddles drag water around with them as they go. Am I right?
Yeah.
You can even think of a whirlpool. So that has a lot of similarities.
It turns out that there's an analog between, say, gravity, the forces of gravity, this curvature of gravity, and how fluid flows. And so if you have an object spinning, it's kind of like if you took a basketball and you put it in a sink and started spinning it, it would drag the water around with it in kind of a little whirlpool-y, draggy thing. And that happens in space-time, too. So a heavy object that's spinning will also have these weird space-time effects as it drags things along in the direction that it's spinning.
You can also, I was thinking more like if you picture a whirlpool, like the sort of scary deep sea funnel things, you could get kind of pulled towards it from far away, and then as you get closer, you get kind of whipped around it too. And that's kind of the thing you feel if you were, say, falling towards a very quickly spinning black hole.
That's a really, I absolutely get that. That's cool.
Yeah.
That's very cool. I have another question.
Okay.
Size, specifically. Is there anything which dictates a uniformity of size to black holes? or can they be of any size? Now, coming at this from a kind of very ignorant point of view, I would have thought that the amount of matter needed to collapse into a black hole in order to create it would create a certain uniformity of size, but I'm not sure if that's the case.
That's a very good question. In order to collapse to a black hole, you just need a certain amount of matter within a certain volume. So it's actually a density that there's a density limit. However, most of the black holes that we know of in the universe have come from stars that have collapsed. And there's also the much larger black holes, which are at the center of galaxies. And these are about billions of times the size of our sun. Black holes turn out to, this is maybe getting a little far afield, but black holes radiate out energy called Hawking radiation. And the smaller a black hole is, the faster that radiation will cause it to evaporate. So very, very tiny black holes can evaporate in the blink of an eye. So you wouldn't expect to see too many of them too long after they've been created.
In classical general relativity, it's actually a deep principle that black holes of different masses have a very simple relationship between their mass and their size. So how far away you are before you start feeling a certain percentage of the effect is a simple scaling. You just zoom in, you zoom out, and you can model a black hole of any mass just by how big you make it.
Wow.
So everything basically depends only on its mass. So
in the classical.
In the classical case.
General relativity. Once you get quantum stuff and Hawking radiation, then you start getting this signature of other things that tell you, give you some real size measurement. But alone, general relativity has no scale, no set length scale that's different from any other.
Got it. Okay, let's bounce onto Hawking radiation for a moment.
Everybody loves Hawking radiation.
I have two questions which kind of instantly present themselves when you mention this. Firstly, what differs about Hawking radiation that allows it to be emitted from a black hole rather than drawn into it?
So there's something called Hawking radiation. And what it is really specific. The idea is, imagine that you have a particle detector, like a Geiger counter, okay? You have a particle detector, it's sitting on your workbench, and your workbench is in a rocket ship. So if you take your rocket ship fairly close to the black hole, you're going to have to turn on your rocket engines to maximum to keep from falling further into the black hole. So you're going to have to accelerate. So your rocket engines are on full blast. You're feeling 800 Gs or whatever. It's 5 Gs. I don't know how big this black hole is or how close you are to it, but you're feeling some acceleration. And what will happen is your particle detector will start going off. It'll start going tick, 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 and measuring particles. There's some question as to whether or not the particles are real or not, because this effect comes from an interaction between quantum mechanics and general relativity. So what Stephen Hawking did was he said, we don't know how to combine quantum mechanics and relativity. We don't know if you have a quantum mechanical electron. We don't know what kind of space-time geometry it's creating because, we don't know exactly where it is or how fast it's moving or anything like that. There's all sorts of limitations on what we know because of quantum mechanics, so we don't actually know what kind of gravity quantum mechanical objects have. But we can say, how does a quantum mechanical field behave in a curved space-time? This is a question we can answer. And so he did this. He put a quantum mechanical field near a black hole, and he found out that if you stand still near a black hole, your particle detector will detect particles in the field, even if there are no actual particles in the field. Right? So there's no electrons streaming by you, but your electron detector will say, hey, I'm measuring all sorts of particles. So this is what Hawking radiation is at its heart. It's if you're accelerating near a black hole, if you're standing at a constant radius near a black hole, you're going to detect particles. And so what people have said is, if there's radiation, it's probably coming from the black hole because the closer you get to the black hole, the more intense this radiation you detect will be. And so if it's being emitted from the black hole must be losing mass as a result. And then there's a question of, so how does the intensity of the radiation emitted depend on the black hole? It turns out that the smaller the black hole is, the more intense the radiation it puts off. And so from that, we deduce that really small black holes will emit a ton of this crazy radiation, and that will cause them to lose mass really quickly.
It might be worth pointing out that we see this outside the black hole's horizon. We're never getting around the standard idea that as soon as something falls into the black hole's horizon, we'll never see anything of it ever again. There's actually sort of a physical interpretation of Hawking radiation, which says that in quantum mechanics, you can just have random pairs of a particle and antiparticle being spontaneously emerging from the quantum foam and then merging back together and disappearing. And then one of the two in that pair falls into the black hole and the other one escapes. And this is how we get these sort of particles being produced out of nothing near the horizon of the black hole.
So this, and again, I'm kind of coming at this from the perspective of someone who watched Doctor Who since he was 10. This would be essentially the event horizon around the black hole would be an area, if not of chaos, then certainly of colossal quantum activity for, as you say, the foam to be sufficiently excited, for want of a better word, to generate these random pairings and to create this probably illusory sensation of Hawking radiation being pushed out from the black hole itself. Am I right?
This is why size matters for this. It's the little black hole that's more active. Oh, yeah.
Do we really want the girl on the podcast saying that?
Look, who else on this podcast is going to say that with authority?
Nicely done.
The point is, though, that if it's the small black hole, you need sort of the comparison of the scale of the quantum activity to the scale of the curvature in the black hole. And if it's little, that becomes more important. If it's an enormous black hole like the one at the center of our galaxy, the sort of at the horizon, the scale is so big that this kind of quantum effect isn't as pronounced.
Got it. How do you detect Hawking radiation?
Any particle detector will be able to detect the Hawking radiation.
Really? So these particles are of such a almost universal nature that anything from, say, a Geiger counter to an old-fashioned analog radio will pick it up as static, something like that?
Yeah, so the deal is that Hawking radiation gets generated in any type of quantum field. So if it's an electron detector, it will detect electrons made in this weird electron quantum mechanical field. So when they pop up due to Hawking radiation, you'll detect them.
You get electrons and positrons.
Yep. So alternatively, yeah. So there's an electromagnetic field that's near the black hole. So Hawking radiation would be generated in that. So those will be photons that we detect. So pretty much any particle detector that we have ends up detecting particles in some kind of quantum mechanical field. And then that quantum mechanical field will get excited by the black hole.
This isn't something we've actually done.
Yeah, it's still a little bit theoretical. And you'll note that when I said that we deduce, there's a small accounting trick there, which is essentially we don't know, I emphasized this before, we don't know how quantum mechanical particles interact with gravity. We know how their trajectories will behave interacting with gravity. So even though we know how the quantum mechanical field will be excited by the black hole, we don't know how the black hole will respond to that excitation, right? Because we don't know how mass is generated and lost due to these quantum effects. So it's kind of still a paradox that the scientific field is mulling over, I guess.
You see, that both neatly cuts off my second question and raises another one. Because my second question was going to be, if we can detect them, then surely that has really interesting implications for galactic cartography, in that you can detect areas where Hawking radiation is particularly pronounced and work out almost the possibility of a kind of a photographic negative of a stellar nursery, places where black holes are very concentrated. But if we can't detect them, or at least if we can't definitively rather than theoretically detect them, my girlfriend is a lawyer, I'm used to linguistic polish, then what is the state of research into how Hawking particles could be theoretically detected? I think would be my next question.
So Hawking radiation from large black holes, like solar mass black holes, like black holes the size of the sun, or black holes the size of, or 10 billion times the size of the sun, the amount of energy coming off that is very, very low. It's actually lower than the temperature of that radiation, if you like, is much lower than the temperature of the universe. So you wouldn't be able to see this. A black hole the size of the sun has radiation coming off it that's only about 100 nanokelvins in temperature. So when you compare that to the temperature of the cosmic microwave background radiation, which is about 2.7 Kelvin, you can't even tell that it's there. So this is something you'd only be able to detect in a very, very small black hole.
Yeah. So incidentally, you know how CERN, people were like, so crazy journalists go up to the physicists at CERN and say, is it possible that CERN will create a black hole? And the people at CERN say, maybe. And that maybe is, they mean probably not, but, there are some really crazy physics theories that allow for the creation of a black hole. And so CERN was looking for black holes because what would happen is if they did make a black hole, it would be so small that it would evaporate all its mass off in Hawking radiation. So they were looking for this Hawking radiation to see if they found it, they would know that it was proof of existence that they were making black holes, which would then confirm these crazy theories.
So in 50 words, you have done a better job of explaining the basic science behind CERN than anyone in my profession did across roughly a 2-year period.
Well, that was only a sort of minor sideline to what they were looking for.
Yeah. All right, that's it.
Okay, 2 things.
What?
We forgot to use our catchphrase. Once you go black hole, you never come back whole.
Oh, that's good.
Yeah.
Almost.
Well, 20% faster, unless he was sitting there talking for a long time. It's like, he was talking for like 4 hours, but it only seemed like 3.
Yes.
Or, okay, that's not 20% at all, but, roughly.
Do you
order of magnitude.
5?
Why don't you say 8 and 10 or something, and then I'll edit it so you got the math right.
So, the doctor was down there talking to Satan for 10 hours, and Rose was only waiting up there for 8 hours. But, that's not such a huge difference that it needed to be plot relevant.
No. He talks to her for 10 hours, and she waits 12 hours.
No, she feels so time's passing slower
time goes
the
faster.
doctor.
Time goes slower for the doctor, yeah.
That's right. So
when Rose looks at the doctor, oh, okay, yeah, I gotcha.
The doctor's been talking for 4 hours. Rose sees it as him talking in like a deeper voice for 5 hours.
Yes.
And a huskier voice.
Huskier voice.
Because we do. Yeah, never mind.
Right. We can talk about Doppler shift now, right?
Yeah, sure.
So why don't you say that so that we can get the numbers right on that?
I can't remember it here, Dave. You say the analogy. I need more coffee.
Does that mean cucumber's a fruit?
Yes, cucumber's a fruit.
Son of a bitch!